So write the equation for the horizontal asymptote if there is one, then graph the rational function and your asymptote to verify your work. Alright, so I notice on this first problem that the degree of the numerator and the degree of the denominator are the same. So with that in mind, as x gets very, very large, these non-lead terms become insignificant and the function acts approximately like 8x to the fourth divided by 2x to the fourth, which simplifies to 4. So I would expect that there would be a horizontal asymptote at y equals 4. So with that in mind, let's see. We need to enter this equation, and you need to make sure you have parentheses around the top and the bottom, or when you enter this in your calculator, it'll do 5 divided by 2x to the fourth, and then add all the rest of the terms. So 8x to the fourth plus 5, close parentheses, divided by open parentheses, 2x to the fourth plus x squared minus 1, and our asymptote should be at 4. So let's take a look. So there is the function, and there's the asymptote, and you can see that as x gets big, the function follows the asymptote out there and there. Next, let's look at this one. Well, this one is in factored form, not standard form. So in order for us to find the horizontal asymptote, we need to find the lead coefficients of the numerator, or the lead terms of the numerator and denominator. So we could do that by multiplying the lead terms. So this would be 6x squared. We don't need to multiply the rest of it out. In the denominator, the lead terms multiplied, so negative 1x squared, and the other terms don't matter. As x goes to infinity, these terms become insignificant, and the function acts like 6x squared over negative 1x squared, and so this simplifies to negative 6. So there should be an asymptote down there. So entering the function, let's see, 3x plus 3, 2x minus 1, divided by double parentheses, negative x minus 1, and x plus 3, close parenthesis. And kind of hard to see there, and I drew the asymptote in the wrong location. So let's go back in. We'll change that to negative 6, and then we'll go to the window, and let's go negative 30 to positive 30 by 5s, and then we'll go down a little bit, negative 20. Let's see if we can see a little better now. Yep, and so where x is large, the function acts like the asymptote, like that. Okay, let's switch to the other side, and we're given this function b of x equals all this stuff. It's a rational function because there's a polynomial in the numerator and denominator. We need to find all of these different characteristics of the rational function. So let's start with the wholes. I don't see any matchers, top or bottom, so no wholes. X-intercepts will be in the numerator, so they're going to occur at negative 5 and positive 4, the roots of those linear binomials. The vertical asymptotes come from the denominator. The roots of those linear binomials are positive 2 and negative 4. Let's see. A horizontal or oblique asymptote is going to come from the lead terms. So we can find those. The lead terms will be x times x in the numerator and x times x in the denominator. As x gets big, all the other terms become insignificant. X squared over x squared is 1, so the horizontal asymptote is at 1. The y-intercept comes from the constants in the rational function when numerator and denominator are in standard form. And we can get those numbers by multiplying these constants. So 5 times negative 4 is negative 20, and negative 2 times 4 is negative 8. So the y-intercept will be at 20 over 8 is positive 2.5. Okay. So, oh, you couldn't see that up there. All right. So now let's graph everything that we know. We know the vertical asymptotes are at plus 2 and at minus 4. And there's x-intercepts at negative 5 and plus 4. And there's a y-intercept at 2.5. And a horizontal asymptote at y equals 1. Now, without graphing, I can guess, based on the intercepts and the asymptotes, that the function must look something like this. Okay. Lastly, the domain. Well, we know the domain for a rational function is all real numbers from negative infinity to positive infinity, except for the discontinuities that are vertical or removable. Basically, the vertical asymptotes are the wholes, and so those would be at positive 2 and negative 4.